Hi, everyone. In this video, we'll do some more example of permutations and combinations, and we have a mix of both. So we're going to be identifying whether the situation describes a permutation or combination, and then we're going to compute it. So our first example, a raffle has 22 people in it, each having one entry. There are 3 winners, each receives an identical prize basket. How many ways can the winners be selected? And so this was kind of tricky. So the first question, as always, that we ask is, does order matter? Okay, and so to answer this question, we can say, what happens if we swap? So let's say the winners are A, B, and C. So person A, person B, person C. Person A gets a prize basket. Person B gets an identical prize basket. Person C gets an identical prize basket. So if we swap A and B, then A is getting the same prize, B is getting the same prize, and C is getting the same prize. So besides the order in which they were chosen, they're all getting the same prize. And so in terms of an outcome, then all we really care about is who wins, who got the prize baskets. These 3 got the prize baskets. Now, if there was a first place winner, a second place winner, and a third place winner, now if you swap 2 of them, there's different prizes, right? If they had, or even if it's not necessarily first, second, and third, maybe it's just 3 different prize baskets, then the order matters. But here, it's just 3 of the same prize basket. And so because all prizes are identical, we only care about who wins and not what order they were chosen. And because we don't care about the order, the answer is no, it doesn't matter. And that means we want to use a combination. And so we have 22 people, and we're choosing 3, so we want to compute 22, choose 3. And I'll use my shortcut method. So 22 permute 3. Well, I shouldn't say it's not mine, but I will use the shortcut method. 22 permute 3 over 3 factorial. So I write up the first 3 terms of 22 factorial divided by 3 times 2. So to simplify this, I know that 21 is divisible by 3, so 21 over 3 is 7. So now I've got 22 times 7 times 20 over 2. And then 20 I could either do 22 over 2 or 20 over 2. I'll do 20 over 2 to get 10. So this is 22 times 7 times 10. And that is 1,540. Now, what I recommend is when you're doing this, unless you're super confident, I would recommend writing this all out each time, because I could have also just done this as well and canceled everything on the one fraction. But unless you're super comfortable with it, if this is new to you, I would write it out every single time you make a cancellation. So I write this and I write the 7, and then I write it out on the next line. Okay. So now, student council is holding elections for president and vice president. There are 18 candidates. Whoever gets the most votes will be the president, and whoever gets the second most votes will be vice president. How many ways can president and vice president be selected? So we ask our question. Does order matter? Well, if I've got president and VP, if person A is selected as president and B is selected as vice president, versus B is selected as president and A is selected as vice president, are these different outcomes? I would say so. If you were A, being president, that's the difference between you being president and you being vice president. I would imagine that makes a lot of big difference to you. And so these are different outcomes. We're not just picking 2 people. We're picking 2 people and then saying one of you is president and one of you is vice president. So it's picking and arranging them. It's not just picking them. Different outcomes, we care about who comes in first and who comes in second. And so does order matter? The answer is yes. So we're doing a permutation. Okay, and so the permutation we're looking for is there are 18 candidates, so that's 18 permute 2. So we just write out the first two terms of 18 factorial, so that's 18 times 17. Which is 306. And so that is the total number of ways to select our president and vice president. Finally, your local ice cream shop has 20 flavors. You want to rank your top 3 favorites. How many ways can you do this? So, does order matter? So this one is a little clearer because top 3, that means your first, second, and third. You want to rank your top 3 favorites. And so, yes, right? If you have a first place, second place, third place, so if you have chocolate, vanilla, and strawberry, this is a different ranking than vanilla, chocolate, and strawberry. By swapping vanilla and chocolate, we've created a different ranking. And whenever you're saying ranking your top 3, that's a very good indication that order does matter. And so here, because order matters, we're doing a permutation. And so the permutation we want to do, well, we have 20 flavors, 20 options. We want to permute 3. We want to rank 3 in order. And so we write out the first 3 terms of 20 factorial. So that's 20 times 19 times 18. And that's 20 times 19 times 18. So that's 6,840. Okay? And so I want to make a comment, or we actually have one more, never mind. A company has a team of 15 people. They need to select 4 people to work on a committee. How many ways can they do this? So, does order matter? Pause it for a sec, think about it. Hopefully you've done so. The answer is no, it does not matter. Why? Because we're just trying to select a group of people. There's no notion of an ordering. If I pick Alfred and then Bruce, that's the same as picking Bruce then Alfred. All we care, so there's no notion of ordering. We only care about who is in the group. Right? We don't care the order that we were selected. We just care how many groups can you make. So whenever you're selecting groups of people, unless there's info or groups of things, unless there's extra information, if it's just how many ways can you pick 3 things out of 10, then order is not going to matter. And so because order doesn't matter, we have a combination. And so the combination we want to do is 15 choose 4. So that's 15 permute 4 over 4 factorial. That's 15 times 14 times 13 times 12 over 4 times 3 times 2. Well, 4 times 3 is 12, so I can cancel the 4 and the 3 with the 12. And then I can, so that's 15 times 14 times 13 over 2. And then 14 divided by 2 is 7. So that's 15 times 7 times 13. And so putting that into my calculator, I get 1,365. Okay, so here's a comment I want to make, comment/observation. So in every single example, of computing n permute k or n choose k, we've always gotten a whole number, right? Not every factorial expression will give you a whole number, but n permute k and n choose k, we had a 1,365, 6,840, 306, 1540. All of these are whole numbers. And in all of our examples in previous videos, they've always been whole numbers. And so this will always be the case. So this should always be the case. These tools count the number of ways to do something. And so it's not possible to have half a way to do something or any other fraction. If I ask you how many ways can you accomplish this task and you say 15.3 ways, that's going to be a little confusing. That doesn't really make sense. And so if you are computing a permutation or combination, and your final answer is not a whole number, this is a good indication that you've made a mistake and need to check your work. And particularly this might happen if you just enter large factorials into your calculator instead of partially expanding. And so, for example, if you're trying to do 750 choose 3, well, that's 750 factorial over 3 factorial times 747 factorial. If I put in 740 factorial, my iPhone literally just says overflow. And so don't try to compute everything, every factorial. You're going to want to partially expand this 750. So that's 750 times 749 times 748 times 747 factorial. Cancel these, and then you can start putting things into your calculator. But if you don't do that, maybe not for 750, but if you did something like 68 factorial, then your calculator is going to round and potentially give you a non-whole number. Okay, so this is just a warning. A warning and a good indication that you need to check your work. But that's all for this video.